Okay, let's do some mechanical stuff. So we've got this model. It's got pore pressures. We've got the properties. All we need to do is specify the mechanical boundary conditions and basically solve it. So let's do a new file, though. I'm going to make a new data file. I'm going to call it, I don't know, mechanical. I'm going to start with restoring the model that we just created. So model restore fluid. Now we really just need to put the boundary conditions on. Seen this before, zone, face, apply, val, x0, range. Here we're going to use the group names. Again, I could have just said x0 and x265 or whatever it is, but we could also say group west 2 or east 1. And if you're nervous about using those names, you can go back and check the model pane. Click on zone face and just double check those names. So this green one is west 2 and this side is east 1. So hopefully that's going to work. And again, if you like, you can rename them in here. And the bottom is just called bottom. So zone, face, apply. And then we're going to fix the x and the y direction. So we just say 0, 0, val 0, 0, range, group, bottom. And now what we're doing is we've already got the pore pressures. We're happy with that. We're just solving for the mechanical part. So what we're going to do now is turn on the mechanical and turn off the fluid. It's straightforward, but there's one extra trick to know. And that is that if you're just doing the mechanical part and you don't want the pore pressures to change, you need to set the fluid bulk modulus to 0. That is because you could imagine, even if we're not doing a fluid flow analysis, we're just doing the mechanical part, things start to move. Let's pretend we're squeezing this thing and there's fluid in there with some realistic fluid bulk modulus. It's going to increase the pore pressure, right? Just due to mechanical effects. So I'm squeezing this thing, I'm squeezing the sponge, the pore pressure goes up, right? If I release the sponge, the pore pressure goes down, just due to mechanical effects. I'm not even calculating flow here, right? It's just because the pore volume is changing, which causes the pore pressure to change. If you're doing a truly coupled analysis, that's what you want, right? That's the true situation. I mean, mechanical changes cause pore pressure changes, and pore pressure changes cause mechanical changes. And you can do a full two-way coupling. And you can do that. It's just slow, right? Because it's doing mechanical steps and fluid steps and mechanical steps and fluid steps, and they're all interacting, and it just takes some time. You know, you'll see a lot of real-life consulting projects that do what we're doing now, which is calculate the fluid only, then calculate the mechanical only. You just have to be careful when you calculate the mechanical only, set the fluid bulk modulus to 0 so it doesn't cause the pore pressures to change. If you don't, it's not a catastrophe. They're probably not going to change a lot, but you never know. In this case, probably not too much. But imagine a situation where maybe you're dropping an embankment on the top or some giant load, and you're going to see a big jump in pore pressure, right? This is the undrained effect, which I'm sure you guys all know about. So you may or may not want to account for that. In this case, we don't want to account for that. So we're just going to say zone, grid point, any fluid mod 0. And I'm going to say model fluid off, mech on. And then I have to specify large strain or small strain. In this case, we can say small strain, so we say model large strain off. And then we give this handy command, model solve elastic. And if you remember, what this does is it turns everything to be infinitely strong, solves it, and then turns everything to its true strength and solves it again. And actually, just for fun, we can take a history here of, just so we can see how this works. Model history, heck. I can't remember what it is off the top of my head. Hold on. I don't have it in my notes. Nope, that didn't work. Model back, yes. I think you can take a history of the unbalanced force ratio, right? So you can see, there we go. So model, history, mechanical, ratio. Do that, model, history. This is just numerical stuff, but it's interesting. I just want to show you, you don't have to do this in a real life project, but model, history, mechanical, ratio. Because what you can do, you'll see the unbalanced solve ratio go down to 1e minus 5 during the elastic part. And then it's going to set everything to be its true strength. And some of the zones are probably going to fail. And so you're going to have an unbalanced force ratio that goes up and then comes back down again to 1e minus 5, right? And the stresses redistribute and all that kind of stuff. So let's put that history on there. We're going to solve it. And we're going to save it. Okay, let's see if this works. Wow, that took like less than 1 second on my computer, which is surprising. Let's go have a look. I'm going to go to zones. Go to this. I'm going to change the contour to displacement. Okay, so I've got a meter of displacement. I can add the vectors. So if I go to the plus, go to vectors. See, so this makes sense because we turned on gravity. We didn't specify any initial stress state. We just let it move, so everything moved down. Fun, I can check the stresses here to make sure everything's okay. So if I click on my zone displacement plot, still doing contour, change it to stress. Let's change the quantity to YY. Let's change the method to volumetric averaging. Hide my vectors. Now I can see bigger compressive stresses at the bottom. Personally, I find this a little bit confusing because the biggest compressive stresses are blue and the smallest compressive stresses are red. So whenever I'm plotting stress, I go in here where it says contour, click the button for reversed. Now I've got the most compressive stresses are red, the least compressive stresses are blue. Oh, what I was going to do is show you the unbalanced force ratio plot. So we can just make a new plot here. So go to the drop down, say new plot, call it like ratio. And then click the little down arrow here next to the plus, the plot item list, and choose history chart. And then click the plus for mechanical ratio limit. Okay, it's not super exciting, but you can see that there's a big unbalanced force ratio to start with, which dropped down and eventually hit 1e minus 5, and then turns everything to be plastic, and you get a little bump. It comes and converges again. And in fact, it's easier to plot this in log space. So if I look at the attributes here and expand where it says axis 2 and click on log, now it's a little more clear. You can see how this unbalanced force ratio decreased down to 1e minus 5. then jumped up again when it did turned everything to be plastic, and then decreased again back down to 1e minus 5. Make sense? Go back to our zone plot. We can just check to see if anything's failing. So click on your zone stress or whatever it is you're plotting. Change the contour back to label. Change the label to state. See that some of these zones are failing. The past, but presumably the stress is all redistributed and everything came back to equilibrium and everybody's happy. So we do not have any sort of catastrophic failure here. So what we can do is if we go back to the mechanical.dat file, just add a couple more lines here. We're going to initialize the displacements back to 0. So zone, grid point, ini, disp, 0, 0. Because we don't care about everything up until now. We just put the gravity on it, move down a meter, right? We don't care about that. But we can see what the factor of safety of this thing is. And just say model factor of safety. I don't want to run the whole file again. I'm going to save this file. I'm going to select those 2 lines that I just typed. I'm going to right click and I'm going to say run selection. That's probably going to take a few minutes because, as discussed, it's running a bunch of models over and over again, and you can see what the status is here, right? So currently it's, at least on mine, it's at 1.09. Oh, didn't take that long. And it does this binary search, right? Where it does a higher factor of safety, then lower, then higher, then lower. Until it gets to some number. I got 1.09. If I double click on the unstable save state, go back to my zone plot, and contour by something, I don't know, velocity. I can see what's happening here. It's actually pretty neat. Kind of finds its way down through the clay layer, or is that the sand layer? Forms this sort of slightly non-circular failure surface, which is kind of fun. And so apparently in the real life project, they did this and got this more or less this answer. Let me scroll forward here. Yeah, okay, 1.09. And what, again, they thought this is pretty close to 1, and probably this thing isn't even necessarily really standing up. And so what they did is sort of went and reevaluated the properties. And they changed the properties of the clay layer such that they have like these undrained properties. And so what they did was they changed the properties of the clay layer such that cohesion changed with stress, right? So increasing cohesion with increasing depth. And for whatever reason, they decided that was a realistic representation rather than just giving it a constant value. So they put in this variable cohesion with stress and ended up with a factor of safety that was close to 1.6. So we're just going to do that. And it's going to require a little bit of fish. So you get to use what you learned yesterday, hopefully. I'm going to make a new file, new data file, and let's call it undrained. I'm going to restore the mechanical state. I don't care about those factor of safety states. That was just a fun side exercise to see what the factor of safety of that model was. I'm going to start back with the solved mechanical model, and I'm just going to change the properties for the clay layer. So I'm going to give myself a comment here that's or change cohesion of clay So this is a relatively uncomplicated little bit of fish here, so hopefully we can follow along. Fish define set cohesion. And then if you remember, looping through all the zones is easy. You just say loop for each some variable name. I like to use ZP for zone pointer, but you can call it whatever you want. Zone.list. When I'm doing this, I often like to put the end loops in and the ends in. So I have the structure here, you know what I mean? And you can even see these little collapsing things. So I've got my loop for each ZP in the zone list and loop, and then inside the loop, I only want to mess with the clay layer. So I need an if statement here. If zone.group ZP. Now remember, we have these different slots. So the slot called block, I think, had all those block names from the sketch. And when we assigned the property names, they went into the slot called construction. So I need to say, okay, if the zone group in slot construction, the syntax is like this. So I say zone group ZP, comma, the slot name. So if the zone group in slot construction equals clay, in quotes, because these are all strings, then I'm going to change the cohesion zone prop ZP, comma, cohesion, again a string. So these property names are strings. So zone.prop for property, zone, comma, whatever property it is we want to change. So in this case, cohesion equals this zone dot stress dot effective dot yy. So what we're taking is the vertical effective stress. But remember that stresses are compression negative. And obviously we don't want a negative cohesion here. So we're going to take negative of the vertical effective stress, that zone, times 0.16. I don't know where the 0.16 comes from. They worked out that the cohesion is 0.16 times the effective stress. And I think the friction is already 0. But I have in my notes here to set the friction as 0. I think it's already 0, but just so I don't deviate from my notes here and screw it up, we can say zone prop ZP. Anybody here like Canadian or British? Does anybody say Z except for me? Everybody say Z. I always say Z by mistake. So friction equals 0. I can say end if. Okay, so that's the fish. We loop through all the zones. If it's clay, change the cohesion. And I think set the friction to 0. I don't think we actually need to do that. And then I need to call the function, which I do by just giving its name in square brackets, right? Set cohesion. And that's it. Now we just do the same thing we did before. So actually we can reset the displacements. Zone, grid point, any disp 0, 0, same thing we did before. In my notes here, I actually have a solve step just to make sure that we didn't totally mess it up. So before we do the factor of safety, it's maybe not a bad idea to do a little solve step here. Probably nothing's going to happen, but we can do it. Model, solve, model. Oh, and actually, we're probably going to use this in the next step when we put the slurry wall in. So we're going to solve it. We're going to save it. Let's call it undrained. And now we can do a factor of safety again. Model, factor of safety. Run this baby. Let's see what happens. No! Didn't like my Did I not save it last time? Oh, I just called it mech. That's why I said. Okay, try again. Okay, I got 1.59. I have a pretty fast laptop. Anybody else get it? So you can go back to your. So see what's happened here is it made 3 new safe states: FOS init 01, FOS stable 01, FOS unstable 01. So it's smart enough if I'm running multiple factor safety analysis to give them different file names, so that it doesn't write on top of itself. This is a situation where you might want to specify the file name by hand, right? You could say model factor safety file, give some name, so you can figure them out later. But if you don't do that, it just automatically puts an 01 on the end, and then an 02, and then an 03. You know, so we can double click on FOS unstable 01. Have a look at our zone plot. Still plotting velocities. You see the same sort of pattern, but now the factor of safety is a lot higher. You can remember, you can add this to the plot. Go to the plus. Under miscellaneous, you can click factor of safety. It'll plot it in the legend here. Just for fun, you can click on FOS unstable, compare to see what difference it makes. Oh, it does make a difference. So you can see that the one we did before, the failure surface is more to the left. The one we're doing now, failure surface is more to the right. So if I was doing this in real life, I would just check the cohesions in the clay layer to make sure I didn't mess it up. So I might click on the undrained.save, which is, we did the undrained solve before we did the factor of safety. And click on that guy. Click on your zone velocity plot item. And under, you can leave it as contour, and under zone value, you can choose property. And under prop name, you can choose cohesion. This is not totally easy to see because it goes from 0 to 126. Instead of color by contour, let's change color to label. Now let's choose property. And now let's choose cohesion. Now you can see this is no longer a contour, so everybody with a different cohesion gets its own solid color. But at least you can get an idea for the range of values in this clay layer here. So all these cohesions depended on the stress, right? And they didn't all have the same stress, so they all have slightly different cohesions here. But you can see that we're in the order of 20,000, so 20 kPa, 21, 22 kPa in this layer. So you can say, okay, well, that's at least reasonable. You could mess around with the contours to try and make this more clear if you wanted to contour it, but you don't necessarily want to spend time doing it. Let's go change it back to contour, property cohesion. And if we go into the contour drop down, change the maximum to like 30,000. Change the minimum to like 10,000. Now you can see. Well, you get the idea. You could mess around with this a little bit more to try and zoom in on the cohesion distribution in this layer. Oh, here's another little trick we could do. I don't know if you guys talked about this, but you can specify what it is you're actually plotting in the plot. So if I choose this zone property cohesion here, and I flip down this arrow, and there's something here called range. If I right click on the range, I can say add range element. So here I can actually range my plot by X coordinate or Y coordinate or whatever. In this case, I'll choose group. So over here on the right hand side, you can double click on group. And now over here under the attributes, it lists all the group names for all those zones. By default, at the top here, it says not, and the not box is checked. So what it's saying is it's not plotting all the things that are checked. Let's uncheck the not, because this double negative is confusing. So just uncheck the not box. Now you can just click the groups that you want to plot. So you need to scroll down here and see if you can find the group called clay. Check that box. So it only plots the clay layer. Now go back up and click on zone property cohesion. Go back to the contour and click the boxes for auto. So it's going to automatically specify the minimum and maximum. So now we see something that's sort of sensible there. Lower. Oh, and I still got this on reverse because I was plotting stress. Uncheck the reverse box there. So now the lower part of the clay layer has a higher cohesion than the top part of the clay layer, which makes sense, which is what we were trying to accomplish here. Note that messing with these ranges, it's only for the plot, right? It's not making my zones disappear in reality or anything like that. They're still there. Just in this particular plot, for this particular plot item, I'm only plotting the clay layer.